Good evening. Let's try finish reading. I just eat my food. I have a bit pain here, so I cannot talk. I like to go to my bed. It's 10 a.m. But let's try finish reading, because if you touch anything you cannot read again. I put the speakers a little bit down because it's 10 a.m. 10 p.m.
Falcon 21++, edit. At a Senate executive session, Air Force acquisition plans and modernization requirements held on the 22nd of April, 1991, Major General Joseph W. Ralston, USAF Director of Tactical Programs, testified that the Falcon 21+& was supposed to have a new fuselage carrying AIM 120 AMRAAMs inside the fuselage. The Falcon 21+& was studied in 1990 as a cheaper alternative to the advanced tactical fighter that became the F-22 Raptor. A blurry image of poor resolution shows the Falcon 21+& had a delta wing and twin vertical tails. The Falcon 21+& was also supposed to be powered by an ATF engine, P&W F119, and an AESA radar with ATF avionics, plus as much observable treatment as could be placed on an airplane like that, according to Major General Ralston. F-16X Falcon 2000, edit. In 1993, Lockheed proposed development of a new version of the F-16. This F-16X Falcon 2000 featured a delta wing based on that of the F-22, together with a fuselage stretched to accommodate the new wing. The F-16X would have 80% more internal fuel volume. The design also permitted conformal carriage of the AIM 120 AMRAAM. Lockheed claimed the F-16X could be built for 2/3 the cost of the F/A-18E/F Super Hornet. NF-16D/Vista/MATV, edit. Main article, General Dynamics F-16 Vista. In the late 1980s, General Dynamics and General Electric began exploring the application of thrust vector control, TVC, technology to the F-16 under the F-16 Multi-Axis Thrust Vectoring, MATV, program. Originally, the Israel Defense Forces /Air Force was going to supply an F-16D for this effort. However, the USAF, which had initially declined to support the program, changed its mind and took over the MATV project in 1991, and Israel withdrew from it the following year. The IDF was involved later when Ilan Raymond, who later became an astronaut on the ill-fated STS-107, flew the MATV F-16 during flight testing at Edwards AFB. Meanwhile, General Dynamics had received a contract in 1988 to develop the Variable Stability in Flight Simulator Test Aircraft, VISTA. The F-16 VISTA effort was funded by the USAF, the US Navy, and NASA. Calspan, a subcontractor to GD, fitted a Block 30 F-16D belonging to Wright Labs with a center stick, in addition to the side stick controller, a new computer, and a digital flight control system that allowed it to imitate, to a degree, the performance of other aircraft. Redesignated an F-16D, its first flight in the Vista configuration occurred on the 9th of April, 1992. In 1993, the variable stability computers and center stick were temporarily removed from the Vista for flight tests for the MATV program, under which the first use of thrust vectoring in flight was accomplished on the 30th of July. Thrust vectoring was enabled through the use of the axisymmetric vectoring exhaust nozzle, AVEN. Following the conclusion of MATV testing in March 1994, the Vista variable stability computers were reinstalled. In 1996 a program was begun to fit the F-16D with a multidirectional thrust vectoring nozzle, but the program was cancelled due to lack of funding later that year. Although the F-16 Vista program was considered successful, thrust vectoring was not taken up for the F-16 by the U.S. Air Force. F-16U, edit. The F-16U was one of several configurations proposed for the United Arab Emirates in the early 1990s. The F-16U was a two-seat aircraft that combined many features of the F-16XL and the delta wing of the F-16X. F-16 Advanced Fighter Technology Integration, edit. In March 1980, General Dynamics began converting the 6th FSD F-16A to serve as the technology demonstrator aircraft for the Joint Flight Dynamics Laboratory NASA Advanced Fighter Technology Integration (AFTI) program. The AFTI F-16 built upon GD's experience with its YF-16 CCV program, and the AFTI F-16 even received the twin pivoting vertical ventral fins from the CCV aircraft, which were likewise installed under the air intake. The aircraft was also fitted with a narrow dorsal fairing along its spine to house additional electronics. Technologies introduced and tested on the AFTI F-16 include a full authority triplex digital flight control system, DFCS, a 6-degree of freedom automated maneuvering attack system, AMAS, a 256-word capacity voice-controlled interactive device, VSED, to control the avionics suite, and a helmet-mounted target designation sight that permitted the forward-looking infrared, FLIR, device and the radar to be automatically slaved to the pilot's head movement. First flight of the AFTI F-16 occurred on the 10th of July, 1982. The Air Force Association gave its 1987 Theodore von Karman Award for the most outstanding achievement in science and engineering to the AFTI F-16 team. The AFTI F-16 participated in numerous research and development programs. 1 AFTI Phase I testing, 1981-1983, a program to review the DFCS system, which undertook analysis of the VSED, to assess the impact of noise and GeForce on speech recognition rates. 2 AFTI Phase II testing, 1983-1987, evaluation of the wing root mounted FLIR and the AMAS system. 3 Autopilot development and testing, 1986-1992. In 1986, members of the AFTI flight test team, in collaboration with General Dynamics, adapted the automated maneuvering capabilities with new ground collision avoidance equations and modified visual and oral cues to develop an automated ground collision avoidance (AutoCAS) system. The system enabled pilots to set a mean sea level or above ground level floor for maneuvering, and included oral and visual warnings as the floor was approached. With no pilot action, the AutoCAS would take over and perform a 5G pull-up. This AutoCAS, which began flight testing in 1987, was intended to help reduce the incidence of controlled flight into terrain, CFIT, accidents. Later versions of the AFTI system included integration with the digital terrain database to provide three-dimensional maneuvering capabilities. The flight test team that developed the system was awarded patent No. US 4924401 in 1990 for this system. This AFTI AutoCAS became the basis for the AGCAS system tested in 1994-96 and later incorporated into the F-16, F-22 and F-35. Forecast /by 1988-1992, a 5-phase evaluation program testing a variety of low-level close air support /battlefield air interdiction, CAS /by techniques, including an automatic target handoff system, ATHS, which transferred target data from ground stations or other aircraft to the aft F-16, and off-axis weapons launch. 5 Talon Sword Bravo, 1993-1994 demonstration of cooperative engagement techniques where the aircraft fires at a target based on targeting information data linked from a distant sensor. The weapon principally investigated was the AGM-88 high-speed anti-radiation missile, HARM. 6 EGI, 1994 and 1997 testing of embedded GPS/INS, EGI, navigation systems, including evaluation of the reliability of GPS in jamming environments. 7 AGCAS, 1994-96 testing of an automatic ground collision avoidance system, AGCAS or AutoCAS, to help reduce the incidence of controlled flight into terrain. CFIT. Lessons learned from this program were further evolved on the F-16 CAS. 8J/IST, 1997-2000 testing of the world's first all-electric flight control system under the Joint Strike Fighter Integrated Subsystem Technologies, J/IST, program. F-16 CAS, edit. Due to the unavailability of the AFT F-16 following the AGCAS effort, a Block 25 F-16D was modified for continued investigation of ground collision avoidance system, CAS, technologies to reduce CFIT incidents. This joint effort by the USAF, Lockheed Martin, NASA and the Swedish Air Force was conducted during 1997-98. It has recently been reported that the U.S. Air Force had decided to upgrade the F-16, F-22 and F-35, all Lockheed Martin designed, fly-by-wire fighters, with the AGCAS system. F-16 Agile Falcon, edit. The F-16 Agile Falcon was a variant proposed by General Dynamics in 1984 that featured a 25% larger wing, upgraded engine, and some already planned MSIP-4 improvements for the basic F-16. Unsuccessfully offered as a low-cost alternative for the Advanced Tactical Fighter, ATF, competition, some of its capabilities were incorporated into the F-16C/D Block 40 and the Agile Falcon would serve as the basis for developing Japan's F-2 fighter. F-16S, edit. The F-16 Enhanced Strategic, S, was an extended-range variant of the F-16C/D fitted with conformal fuel tanks that granted it a 40% greater range over the standard Block 50. The F-16S also featured an internal FLA system, which offered the capabilities of the Lantern navigation and targeting system without the drag associated with external pods. Unsuccessfully offered to Israel as an alternative to the F-15I Strike Eagle in late 1993, it was one of several configuration options offered to the United Arab Emirates that would ultimately lead to the development of the F-16E/F Block 60 for that nation. An F-16C Block 30 was modified to the S configuration to test the conformal tanks and simulated FLA sensor turrets fitted above and below the nose of the aircraft. The F-16S first flew on the 5th of November, 1994 and flight testing was completed in January, 1995. F-16 Low, edit. The F-16 Low Observable Axisymmetric Nozzle, LOW, demonstrator was an F-16C fitted in late 1996 with a prototype nozzle with significantly reduced radar and infrared signatures and lowered maintenance requirements. It was tested in November 1996 to evaluate the technology for the Joint Strike Fighter, JSF, program. F-16D CK-1, edit. Manet, the Israeli Air Force's Flight Test Center, is known to operate a specially built Block 40 F-16D delivered in 1987 as a test aircraft designated CK-1. It is used by the IAF for testing new flight configurations, weapon systems, and avionics. F-16 DSI, edit. The DSI concept, diverterless supersonic inlet, was introduced into the JAST/JSF program as a trade study item in mid-1994. The first Lockheed DSI was flown on the 11th of December, 1996 as part of a technology demonstration project. A DSI was installed on an F-16 Block 30 fighter, replacing the aircraft's original intake diverter. The modified F-16 demonstrated a maximum speed of Mach 2.0. Mach 2.0 is the F-16's clean certified maximum speed, and handling characteristics similar to a normal F-16. Subsonic specific excess power was slightly improved. The trade studies involved additional CFD, testing, and weight and cost analyses. A DSI was later incorporated into the design of the Lockheed Martin F-35 Lightning II after proving to be 30% lighter and showing lower production and maintenance costs over traditional inlets while still meeting all performance requirements. Engine variants, edit. F-16/79, edit. In response to President Jimmy Carter's February 1977 directive to curtail arms proliferation by selling only reduced capability weapons to foreign countries, General Dynamics developed a modified export-oriented version of the F-16A/B designed for use with the outdated General Electric J79 turbojet engine. Northrop competed for this market with its F-20 Tiger Shark. Accommodating the J79 GE119 engine required modification of the F-16's inlet, the addition of steel heat shielding, a transfer gearbox, to connect the engine to the existing F-16 gearbox, and an 18-inch, 46 centimeters, stretch of the aft fuselage. First flight occurred on the 29th of October, 1980. The total program cost to develop the F-16/J79 was $18 million, 1980, and the unit flyaway cost was projected to be about $8 million. South Korea, Pakistan and other nations were offered these fighters but rejected them, resulting in numerous exceptions being made to sell standard F-16s. With the later relaxation of the policy under President Carter in 1980 and its cancellation under President Ronald Reagan, no examples of either the F-16/79 or the F-20 were ultimately sold. F-16/101, edit. In February 1979, General Electric was awarded a $79.9 million $271 million in 2023, 1979, contract under the Joint USAF/Navy Derivative Fighter Engine, DFE, program to develop a variant of its F-101 turbofan engine, originally designed for the B-1A bomber, for use on the F-16, in lieu of the standard P&W F-100, and the F-14A, in place of the P&W F-30. The first full-scale development, FSD, F-16A, serial number 75-0745, was fitted with the F-101X DFE engine and made its maiden flight on the 19th of December, 1980. Although the F-101 performed better than the F-100, it was not adopted for use. However, data from testing the F-16/101 assisted in the development of the F-110 turbofan, for which the F-101 would serve as the core, and the F-110 would become an alternate engine for both the F-16 and F-14. Proposed and other variants, edit. Bout Model 1600/1601/1602, edit. Main article, Bout Model 1600. The bout/General Dynamics Model 1600 was a navalized derivative of the General Dynamics F-16 fighting Falcon designed for the United States Navy's Navy Air Combat Fighter (NACF) program. The Model 1600 lost to the Northrop/McDonnell Douglas F/A-18 Hornet. F-16BR Block 62 plus Super Viper, edit. For the FX-2 fighter program for the Brazilian Air Force, Lockheed Martin offered the F-16BR Super Viper. The F-16BR is based on the F-16E/F Block 60 and features conformal fuel tanks, and /APG-80 AESA radar, GEF-110-132 engine with FADEC controls, electronic warfare suite and infrared searching, IRST, updated glass cockpit, and a helmet-mounted cueing system. F-16BR lost in the competition with JAS-39 Gripen E. F-16 in Block 70/72 Super Viper, edit. See also, Indian MRCA competition. Lockheed Martin has proposed an advanced variant, the F-16 as its candidate for India's 126 aircraft Indian Air Force Medium Multi-Role Combat Aircraft, MERCA, competition. According to Chuck Artymovich, the company's business development director for the program, the F-16 is the most advanced F-16 ever. Notable F-16 features include an APG-80 active electronically scanned array, AESA, radar, advanced electronic warfare suites, and an infrared search and track, IRST, system. In addition, the F-16 SRCS is reduced from 1.5 m to 0.1 m, in the same class as the F-18 Super Hornet, Rafale, and Eurofighter Typhoon. If selected as the winner of the competition, Lockheed Martin will supply the first 18 aircraft, and will set up an assembly line in India in collaboration with Indian partners for production of the remainder. The program is reportedly worth up to Rs $550 billion, $14 billion. The F-16 Super Viper was showcased in the Aero India, 2009. India initially sent the RFI for an F-16C/D Block 52 plus configuration aircraft for the ongoing Indian MRCA competition to supply the Indian Air Force with 126 multi-role combat aircraft, to replace the Indian Air Force's fleet of MiG-21s. On the 17th of January, 2008, Lockheed Martin offered a customized version of the F-16. The F-16 Super Viper for the Indian MERCA contract. The F-16 which is similar to the F-16 Block 60, will be a 4.5 generation aircraft. Lockheed Martin has described the F-16 as the most advanced and capable F-16 ever. Based closely on the F-16E/F Block 60 as supplied to the UAE. The features on the F-16 include conformal fuel tanks, CFTs, and /APG-80 AESA radar, GEF-110-132 engine with 32,000 pounds, 143 kN, of thrust with FADEC controls, electronic warfare suite and infrared search and track, IRST, advanced all-color glass cockpit with 3 large displays, and a helmet-mounted cueing system. Lockheed Martin's Vice President Business Development, India, Phil Prince has said that I can assure you, the Super Viper is much more advanced in all aspects than the Block 50/52 plus F-16s being given to Pakistan. In September 2009, F-16 Super Viper completed a part of the field trials. Lockheed Martin officials stated that Phase I of field trials was over and the week-long training phase was in preparation for Phase II of field trials, which began the 7th of September and lasted 2 weeks. Eventually, the F-16 in Super Viper lost out to the French Dassault Rafale fighter. It was reported the 21st of September, 2012 that the Indian Air Force would finalize a contract to purchase 126 French Rafale jet fighters that year, in one of 2012's largest armament purchases. The contract for the 126 Rafale twin-engine, Canard Delta Wing, multi-role combat aircraft is worth $20 billion. Indonesian news service reported. In 2015, after the Rafale order was cut back to just 36 aircraft, Lockheed was offering India the exclusive opportunity to produce, operate and export F-16 Block 70 aircraft. In 2017, the F-16 lost in the competition with JAS-39 Gripen E, when Lockheed retired from production in India and decided to move its production line from Fort Worth, Texas to Greenville, South Carolina. As of 2017, Lockheed Martin has agreed to sign a letter of intent with the Indian defense firm Tata Advanced Systems Limited to manufacture the jets in India if the Indian government accepts their tender for India's request for a purchase of single-engine aircraft to replace its aging MiG fighters. The new production line can be utilized to supply jets to India as well as for exporting them overseas. On the 19th of June, 2017, during the Paris Air Show, Tata Advanced Systems Limited and Lockheed Martin signed an agreement to produce F-16 Block 70 aircraft in India under the latter's offer to provide the jet to the Indian Air Force under Merca. F-21, edit. Not to be confused with IAI F-21 PFA. After cancelling the Merca tender, the Indian Air Force launched another request for information in April 2018 for another tender for around 110 aircraft, which was unofficially referred to as MRFA. Meanwhile, Tata Advanced Systems Limited and Lockheed Martin signed another agreement to produce F-16 wings in India on the 4th of September 2018. As of September 2019, the prototype wing from the Indian facility would be delivered by 2020. The wing prototype made in the Hyderabad facility of Tata Lockheed Martin Aerostructures Limited, TLM, was delivered and certified in December 2021, paving way for the facility to be the sole provider of F-16 wings to Lockheed Martin. The wings were described as a fuel-carrying 9G, 12,000-hour, interchangeable and replaceable fighter wing. It is the same facility which is also the sole provider of empennages of C-130J at a rate of 24 units per year and produced 85 units by April 2018. Lockheed Martin unveiled the F-21 concept at the Aero India Air Show on the 20th of February 2019. The F-21 would include 114 Indian-specific enhancements. Lockheed Martin had offered the F-16 variant earlier in the Merca tender and has replaced the offer with the current F-21, which is to be built in collaboration with Tata Advanced Systems in the available Hyderabad facility. Specific enhancements and changes of the F-21 aircraft includes 1. Avionics, Northrop Grumman and /APG-83 Scalable Agile Beam Radar, SAB, AESA radar with high range, more targets and higher precision coupled with long-range infrared search and track system. 2. Advanced cockpit, a large area display and a 6/8 center pedestal display similar to the ones on Lockheed Martin F-35 Lightning II as against the F-16 Block 70 variant. 3. Weapons capacity, 40% higher payload capacity with options for 1 triple missile launch adapter on each wing. 4. Decoy, capability to carry an forward/AL-50 towed decoy system on wing pylon as well as tail section. Block 70 variant would only carry TDS on wing pylons. 5. Airframe, redesigned dorsal fin. A service life of 12,000 hours. 6 power plant, General Electric F-110 GE132 engine. 7 aerial refueling, options for both probe and drop and flying boom with added conformal fuel tank for high range. KF-16, edit. RCAF KF-16 at Eielson Air Force Base. Korean Aerospace Industries, KAI, produced 140 KF-16C/D Block 52 fighters under license from Lockheed Martin in the 1990s.